Okay, last time we have a question for you to think. Okay? Like this, if we do this in the lab, and we have a 10-volt source, and we have two identical resistors in a series, and theoretically, if we calculate the voltage on each one, it's supposed to be 5. Right? But if you use the voltmeter to measure it, the first one is showed 4.04, the second one is also 4.04. And you add up together both, then equals 8 something. That means KVL does not satisfy. So what's the problem here? Anyone want to explain?
One resistor. No, something's wrong with it.
Why is not working? I say both working. No problem.
They work.
So what is the problem? What? Any other reason?
The voltmeter had a resistor in parallel with the other one.
What is in parallel with
Voltmeter was
the meter is parallel with
it's connected parallel.
Okay, yes, that is perfect explanation. The meter is in parallel with the measured resistance. So this is a loaded voltage divider. Right? It's not a traditional voltage divider. This is loaded. That means we have a load in parallel with the voltage divider. Right? And in this case, if we have a meter parallel with this 470, if we calculate the voltage drop, we should use the parallel of 470 along with the input impedance or input resistance of the meter, usually like several mega ohms. And these two in parallel. And we know if two resistors are in parallel, the total resistance will be smaller than either one. Right? So the resistance will be smaller than 470. So that means the voltage drop will be smaller than half of that. And it will be 4 point something. Right? So that is correct. Right? And in this is 4 suppose it's 4 volt. If you measure the top one, still the same thing, still 4. But if we measure this one equals 4, then at this time, what is the top voltage? 5.96. Okay, so we 5.96. Yes, okay, we approximately equals 6, right? The bottom is 4, then the top is 6. Oh, now we have an interesting problem. If you have an identical meter like this to measure the top voltage at the same time, what are the readings? The same with what? We have 4, we have 6, we have 5. Theoretically, each one is 5. But if you measure it like this, it is 4. You measure the bottom one, it is 4. And the top one, he just said, okay, equals 6. Yes. And if you measure the top only, the top will be 4, then the bottom will be 6. Now my question is, if you measure both at the same time with two identical meters, what are the readings? 4 and 4. Then that means KVL does not satisfy, right? 4 is not equals 10. 5 and 5, right? Yes or no?
Yes.
Yeah.
Why is 5 and 5?
It was 10.
Because 470 parallel with this meter is the same thing as the top of 470 parallel with the other meter. Okay? So both resistors, the parallel will be smaller, but they are still identical. Does it make sense? For example, 470 parallel with the meter, suppose equals 400. Then the bottom is 400, the top is also 400. Then these two are still identical. Then they share the 10 volts, so each one gets 5. So can you explain what happened? We already explained. Today we are going to, any other questions before we discuss new things? No? Good? This circuit is called Wheatstone bridge. Right? It has a source, it has 4 arms of resistors. And R1, R2, R3, R4. It's connected like this. And in the middle of R1 and R2, and also R3 and R4, we have these 2 nodes we connect to a load. Right? So this is it's called output. And this circuit is called the bridge. Usually, one of these one of the resistors will be variable. The purpose is we can change the value of this R2 and make this output voltage here equal to 0. So if you have a ammeter here, connect to this, we measure the voltage, we measure the current will be equal to 0. In other words, this potential here will be equal to the potential here, or the voltage drop between this point and this point will be equal to 0. And this, in that situation, this bridge is called the imbalance. In the balanced situation, this voltage times this voltage, this resistance times this resistance will be equal to this one times this one. So this is the condition for this bridge to be balanced. The cross product is diagonal, this multiply equals this multiply. Right? So if we know 3, then we can find the other one. Okay, now this one. What is R2? The bridge is balanced. How to calculate this? Tell me the formula first. R2 equals R2 equals R3. What's the formula? When this bridge is balanced, we just mentioned the formula, the condition. What is it? The product of the diagonal must be equal. So that means R1 times R4 must be equal to R3 times R2. So that's the first formula you need to give me. The second one is R2 will be equal to R1 times R4, then divided by R3. The second formula, derived from the first one. Then you plug into numbers. So this one will be equal to 470 times 270, then divided by 330. And the result will be equal to 384. Any questions on this? If you have calculator, you can double check this. Okay, next one is one of the most important theory. We are going to use this for DC circuit, AC circuit, or even advanced circuit analysis. It's called Thevenin's Theorem. Thevenin's theorem states that any two-terminal resistive circuit, actually not necessary, but in this class, it's a resistive circuit, means only deal with resistors, can be replaced with a simple equivalent circuit. That's the topic, equivalent circuit. When we use from two output terminals, the equivalent circuit will look like this. And there's a source, it's called Thevenin's voltage, VTH. And there's a resistance, it's called Thevenin's equivalent resistance, and RTH also. I will explain a little bit more. So first one, let's see what is the VTH. It's called Thevenin's source, but how to calculate this? It is the open circuit voltage looking from that two terminals. So you need to memorize it. Open circuit voltage. So that is VTH. Defined by the open circuit voltage between the two output terminals of the circuit. What is RTH? That is the equivalent resistance appearing between the two output terminals when all sources have been replaced by its internal resistance. Or ideally, just the sources will be reduced to 0. And the total resistance is the Thevenin's resistance. First of all, you need to memorize this definition, and we are going to use the example to show how to apply this. So what is the Thevenin's voltage? I draw the circuit. So suppose like this, we have a circuit, no matter how complex it is, like this, okay? We may have more, and like this, a lot. But we going to have a load here. This is RL. Inside, we don't care. It's very complicated, it can be. Maybe we have another source here, or another battery. What I do is I'm looking from this terminal A and B to this side, looking to this way. We stand as the load. Then this part can be reduced to an equivalent Thevenin circuit. And all this circuit is equivalent to a source here and a Thevenin impedance, resistance, just like this. From this is A, this is B, this is B, this is A. All this part, no matter what we have inside, will be equivalent to 1 voltage, which is called the Thevenin source, and there's a RTH. Definitely we can connect this like this here. Does it make sense? So any complicated circuit, except from the load, will be reduced to an equivalent circuit, which can be represented by only one source and one resistance. This source is called the Thevenin voltage source, and this resistance is called the Thevenin equivalent resistance. Yes.
So, like, when would you use that? Because don't you need to know that all those resistances are there, even if they are?
Yes. If you want to reduce this one, we need to know this.
Right.
But the question is, for example, I ask you, what is the power on this one? You want to directly calculate this, you know that's very complicated, right? Suppose I give you this one equals 1, 10, or I'll give you all the values. But what I want is, I only want to know what is the power dissipated on the load. That's the only thing I need to know.
So why would you use that bottom one other than just to just go ahead and calculate it, like to write it out? Would you use that bottom one?
This one is the reduced, easier to understand.
What would you use that for, though?
Theoretically, we can calculate this and calculate this.
Okay.
And in real life, sometimes this box is complicated. You don't know what is inside.
Okay.
What we do, we cannot calculate because we are not given all these numbers. Okay. What we do is we can measure this one and this one. So we reduce that box like your computer, okay? Black box.
I got you.
Totally only this and this. Then you connect your load to this, you can calculate because we care about the load. We do not care about the inside. I want to know what is the voltage on the load, what is the current flowing through the load, or what is the power dissipated on the load. That's the only thing we need to know because this is the load, right? Inside, that's the internal circuit. We don't care.
Okay.
But I need to know this equivalent source and this equivalent resistance. So that has a very practical usage. And theoretically, yes, sometimes you can directly calculate from here, or usually we prefer to reduce to this simple circuit. Any other question? That's very good. Right? So in real life, most probably you are going to measure this one. You cannot calculate this. For example, if we have like 1,000, 1 million components inside, you cannot calculate this, right? The only thing we can do is you measure this. Okay, any other questions? Right, theoretically, we can reduce all these parts into this one. It's very simple. One is the source, one is the resistance. Now, what is this source? How to calculate this one? This one is defined by the open circuit voltage at these two terminals. Open circuit, okay? Yes, I just disconnect this load here. Right? Disconnect this load like this. This is called the open circuit. The circuit is open from the load. Right? Then you calculate what is the voltage here. If I give you this circuit, you need to calculate, right? In real life, you just measure this. As easy as this. Right? So that is called open circuit voltage at these two terminals. Any question on this? So in real life, it may be easier to just measure this. Right? But in this class, we are going to calculate it. That's the first one, right? Open circuit voltage. What is this one? Thevenin resistance. It is the total resistance looking through this to this way, when all the sources equal to 0. Right? This voltage source, right, we just reduce to 0, nothing. If you have another one here, right, you just make this 0. Then this one has only a network of resistance. So we can calculate the resistance, right? Parallel, right? Series, combinational, no matter what, we can calculate the equivalent resistance. And then that resistance, total resistance, is equal to this one. Once we get this, then we connect to our load. The circuit is as simple as this one, series circuit. Any questions on this? So we know why we want to do this, and we know the definition. Right? How we do this? What is this? This is open circuit voltage. What is this? This is the total resistance looking into the network from point A and B when the sources are equal to 0. When we set the sources equal to 0. Right? Next one we are going to use an example to show how to do this. Okay, like this. That circuit is very simple. Right? As you said, you can directly calculate this, but we still apply this principle here. We have a source here, 12, and we have 10K here and 27K here. And we assume this is the load. From point A, point B, that side, we think this is the box. We don't know that. What I want is I want to reduce this part from these two terminals to the left, reduce to a Thevenin's equivalent, which means I need only one source like that, only one resistance like that. So anybody understand the question? For example, I want to know what is the current here. Right now, we have a lot of ways to calculate this current, right? Directly from this circuit. But we want to use the principle of Thevenin's equivalent. Reduce this part first, then calculate this. Does it make sense? The first one, we calculate the Thevenin's voltage source. Step 1, what is it? We need to calculate the open circuit voltage. So step 1 is make this open. Open means you disconnect from here, disconnect here. So this part is gone, right? Don't even look at this. And what is the voltage between this and these two terminals? What circuit is this? After disconnect this part, what circuit is this?
Series.
That is a very simple series circuit. And this is a voltage divider. Yeah? Right. This is the voltage we want, right? So what is the voltage? What is it? So Thevenin's source equals the open circuit voltage. We open the load. What we have is we have this only, right? And this one equals Vf, and this one equals R1, R2, R1, R2. And what we want is this open circuit voltage here. What is this? This equals what? This is voltage divider, right?
Yes.
What's the formula for voltage divider? Vs
Times O.
R2 on the top, because we're interested in this, right? And the bottom is R1 plus R2. And that one equals 12. And on the top, that is 27. And on the bottom is 10 plus 27. What's this value? 12, 8.
8.7.
Okay, 8.7. Okay, we just use 2. So 8.7. So we have done this. That's the step 1. What's the next one? What we are looking for next? R, yes, Thevenin's equivalent resistance. All right. Step 2 is RTH. What is this? That is the total resistance. Look, still the circuit is open, right? We don't care of the load. Just like simple as this. The total resistance looking into the circuit from A this to this way when the sources are equal to 0. So this one, what is the source, right? Will be replaced by a straight line. So what we have is the circuit will be like this, a straight line here, like this. And you'll be looking to this way. What circuit is this? Series? We are looking the total resistance from this two terminals to the left.
But connecting also two also resistance when it be parallel.
So in parallel or in series?
Both.
This is R1, this is R2.
Both?
Both? Parallel and in series?
Yeah.
How can you connect in both parallel and in series?
Because your two terminals are up and bottom, so looking from that point of view, it would be a parallel circuit because of the two terminals.
This is a straight line, right? So this two, this part just connect to this one, and this part connect to each other.
Oh.
So R1 and R2 in parallel or in series? We are looking from this A and B. Looking into here. Parallel?
It's just not the way we look at it.
Right? I make this one because this is straight line, right? Okay, I will move like this. It's good? I didn't change anything, right? I just bent that one to like this. So this parallel or series?
Parallel.
Hello?
It was in series.
Series?
Yes.
No, it's parallel.
We're looking from this A point.
Now
right?
it's parallel after you did that.
We're looking from this side to the left.
It basically is in both
So they are in parallel or in series?
Parallel.
parallel.
Series.
No, parallel. Because you have two nodes.
Alright, let me draw this better, alright?
Oh, yeah. I got my terms backwards.
We are looking from here, this way.
Parallel.
Parallel.
Parallel, right?
Yeah.
Hello?
Yeah.
Yeah.
It's parallel. Because you have A.
Parallel or series? Hello? Parallel or series? This is parallel, right?
Yes.
Okay, so that will be equal to R1, R2 in parallel. That is what I want. You don't need to give me the reason, right? It's just like this. So that one will be equal to 10 and 27, right? So 10 times 27 over 10 plus 27. Yes? Okay, equals what?
7.29.
7.29. Okay, we use 7.3. Eh? Okay, we are done with the equivalent circuit. So can we draw the equivalent circuit? The equivalent circuit will be, we have a Thevenin source, this is VTH equals what? Right, the circuit will be like this one. Right? Or this part, we have two resistors, one source will be reduced to this one. This source equals what? 8.7, and this resistance equals 7.3. So RTH equals 7.3 K, right? And now, definitely we need to connect back to our load. Suppose this one equals no matter what equals, we know that. Okay, 68 K. Right? For example, if I ask, what is the load current? What is the current flowing this? What is this one here? Load current. It's easy to calculate, right? How to calculate this current? Use this one. So the load current will be equal to VTH divided by RTH plus the load. This one is, what circuit is this? Series circuit. All the current will be the same. Right? So this current will be equal to total source divided by this plus this. Right? So that is the way how we use a simplified Thevenin's equivalent circuit. Any question? How to do this? Give you a circuit. How to find the Thevenin's equivalent circuit? How many numbers do we need to calculate? Two, right? One is the source, another one is the resistance. How to find the source, VTH? Step one, you open the circuit. Keep in mind, if you do not open the circuit, you are going to do a lot of work and without any result. Right? Okay, the first one is cut, disconnect the load, and make the circuit much easier. Disconnect the load, first step. Second one, calculate the voltage drop, or the voltage looking into the circuit from this 2 points. And in this case, that is just the voltage drop on the R2. Right? So that's it. That's the second step. The next one is to calculate the Thevenin's equivalent, RTH. What is this? Still, we need to disconnect the load. Second, we need to make the load, the sources equal to 0. Like in that 12, we just replace it with a straight wire. The battery is not there anymore. It is a straight wire, not open. Keep in mind, not open. If you say this one is open, this is gone, then that's not correct. For voltage source, we need to make this short. And later time, we are going to learn if for current source, we are going to open it. But for voltage source, we are going to short it. Then you calculate the total resistance using the techniques we learned. Okay, series circuit, parallel circuit, and combinational circuit. Then you calculate the total resistance. Once you get these two, the circuit is reduced. No matter how complex this is, it's reduced. One source here, one resistance here. That's it. Then you connect your load chain into a very simple voltage divider or series circuit. So the voltage equals 8.76, and the Thevenin's resistance for this circuit is 7.3. We calculate this correct. Any questions about this? Before we apply this Thevenin's equivalent to this Wheatstone bridge. Right? This one is not easy to see this. Right? And I'm going to use a method that are different than in the slide. The slide is weak, but I think this is more complicated than my method. What I want, this is the load. The load here. We're interested in here. Then all this, and this source is complex, is more complicated than that one. Right? But I will consider that one as a Thevenin's equivalent. Still, I want to reduce everything to this and this, then my load is here. Does it make sense? Okay, now, what is the Thevenin's resistance? Thevenin's voltage here. I will draw the circuit. This is A, this is B. First one, I disconnect the load, right? The load is gone. Just like this. Step one. Then I need to find the Thevenin's source, the voltage source. By definition, that is the open circuit voltage at point A and B. So that is open circuit voltage. I already opened the load, so that's it. How to find the voltage from here to here? So this one equals Vf. Again, this one circuit looks like a very complicated. We need to simplify, reduce. This is a combinational circuit. Anyone have a better way to see this? Looks like this one. Let me do this. This one is R1. What's next? R3, and R3, R2, R4, like this. So I said this is R1, this is R3. Is this good?
Yes.
For this part, see, connected to this one to like this. It's good, right?
Yeah.
All right. Then this one still the same point, and this one will be R2 here, and this one. Keep in mind, this one is disconnected, so this is not connected anymore. And this one will be equals R4. I'll redraw this like this. Is this good?
Yeah.
This is better to see this, right? This one is a square, this one is like a... So now you know how these four resistors are connected. These two in series first, these two in series first, then these two combinations in parallel. Right? What do we want? We want to know the voltage between here and here. So this is the open circuit voltage. So we want to know this is A, B. Right? VAB. Now we need to recall at the very beginning. VAB means VA minus VB, right? Remember we used the example said this is the floor, okay? So from this floor to that floor. Remember that? So VAB means VA minus VB. Right? So I want to know the voltage at this point, then minus the voltage at this point. That's good?
Yeah.
Right? What is the voltage on here? Okay, we assume this is ground. These two are in parallel. If I remove this one, we do not affect this part, right? Because they are in parallel, the same thing. This same voltage applied to this and up to this. They separate. Does it make sense? So what is the voltage here? What is this?
Yes.
Again, voltage divider, right? So the voltage here will be equal to Vs voltage divider
R2
times R3 over R1 plus R3. That is this one. Then minus VB is here. And now we are interested in this, so you can't forget this part. What is this? Still the same thing, right? Voltage divider. So this one will be equal to Vs times
R4.
and R4 over R2 plus R4. Okay, you can move Vs outside and then combine this one. But anyway, once we know all this resistance, we can calculate this voltage. So that's it. That is the Thevenin's voltage. Right? We are given all. Okay, so the example is on the next. Right? So this calculated the. That is this. Does it make sense? What's the next one? So we done this. Right? The second part is RTH. What is RTH? What's the definition? The total resistance when the load is set to 0. Right? So this one will be equal to 0. Right? That 0 means is like that. That means open. No, that's not correct. We need to short this. That's totally different. If this is open, then it's short, they're different. Now, this circuit is very interesting. What is the total resistance looking from here to the other side? Remember, there's a homework. That's number 4. The circuit is very complicated. You need to redraw this one. It's very similar to like this. You already done the homework, right? So what is the total resistance looking from A and B inside to that circuit? So we need to redraw this. So A is here, B is here. Look at A. This one, what I said is, this one is node is ground. So you look at this one. This is A, this is B. How is R1 connected?
With what?
It is connected between A and ground, right? Right? So R1 is this to the ground. So this is ground. So this is R1 between A and the ground. How about R3? Between A and the ground. Right? So that means this one is also like this. R3. So that means these two are in parallel, right? Right? Now B is and R2. How is R2 connected? Right? B is suppose B is here. Where's how R2 connected? Between B and A. And A is here.
No,
This part
ground.
is ground, right? So this one here is ground. Also ground, all the ground are the same, right? Right? So this is R3. Sorry, R2. How about R4? So also ground. This is R4. What we are looking for? We are looking at the total from A to B. Can you see how these are connected?
Yes.
What I want is what is the total? That's the R, A, and B. From A to B. Right? I make this one easier. Right? Let me see. I draw this one. I bend this one all the way down to here. Because this is just straight wire, like this. So how these 4 resistances are connected? Parallel. All 4 are parallel?
Yes. No.
You trace from, you think the current flowing through A to B.
Combination.
How are these connected?
It's from A to B.
These 2 are in parallel, right? These 2 are in parallel, right? And how about this combination and this combination?
Series.
In series,
So combination.
right? So this is definitely combinational circuit. So these 2 in parallel, these 2 in parallel, then altogether they in parallel, in series. So what is the resistance here? What is it? 1 and 3
1 and 3
in parallel.
plus 2 and 4.
Plus,
parallel.
perfect. Plus means this is in series. Plus 2 and 4 in parallel. Alright, that is the total resistance. And if we are given all these numbers, we can easily plug in and calculate this. And we calculate with TH and RTI. That is a combinational circuit. And we need to know how to reduce the circuit. Like this, the trick is, you know this is ground, right? What is this point? And ground, you rewrite like this one. Because this one, I cannot see how these are connected directly to this. I prefer like this way. And then I bend this one so I can see clearly. These two in parallel, then these two in parallel, like this. Like this. This is A, this is B. The circuit is this one. This one is much better, right? These two in parallel, these two in parallel, then in series. How to get this from here? How to get this from here? The trick is A is here. Now you look at how 1 is connected. It is connected between A and the ground. So you connect 1 from A and to the ground. So you redraw like this. Then how about 3? 3 also from A to the ground, right? So that means from A to ground, just like this. Now you know these two are in parallel. This one is not easy to see, right? Because they are separated far away. But actually these two are just one point. So this is in parallel. And for this same thing, this is B, so B is here. B is different than A. So you cannot connect these two. B is different than A. And this R2 is connected between B and somewhere, oh, it's ground. So from R2 to ground. All ground are the same, like this. And this R4 also point B to ground, so 4 to the ground. So I reduce this circuit into this. Not to reduce, just to redraw this. And keep in mind, what we are looking for is the total between A and B. So the current go this way, definitely this two are in parallel, then pass through this single line, then go this way. So exactly like this. Go this. So this is the R1, this is the R3, this is the R2, this is the R4. Like this. Any question on that? It's hard, right? The only trick I showed you here is, I don't know, you use this method to do the homework number, the last homework, not this one, and the homework before this. That's a very complicated circuit that asks you to calculate some voltage. You may already done this. So this is the real example. We know the Vs equals 10, 15, and that. So we plug into numbers. The circuit will look like this method. They use a different way. What different way? They look at this point. They disconnect this one. That's for sure, right? Because this is load. They separate this circuit into two equivalent circuits. That's why I think this is too much. We only use one equivalent circuit. This one is from this point to the ground considered as one equivalent circuit. So you ignore this, ignore this. You only consider this part. Maybe this one is easier for you to think. Well, let's try. You ignore this, because first time we disconnect this one. Right? We ignore this, ignore this. You only consider this part as a one equivalent circuit. So let me redraw the circuit. It will be like this. This one is gone. Like this one. The equivalent circuit is between this A and the ground. We already disconnected A and the ground, right? So that's the open. What is the VTH here? What circuit is this? Series circuit. So what is divided? So that one equals VS times R2, R1 plus R2. Right? Then, that's it. What is RTH? Make the source equal to 0. This one will be split wire. How these two are connected? R1 and R2. You're looking from these 2 points in this way. How R1 and R2 are connected? In parallel, right? Because this one here, again, just like in our example discussed, right? These two are actually the same ground. So that's why R1 parallel with R. R3, right? This is R3. Right, that's it. So I draw the circuit, looks like we have a source here, and we have this. So, and this is A, this is the ground. We can calculate this, which is VTH, and this is RTH. And we said we have two equivalent circuits, so I put one here, one here, one here, one here. For this one. This is easy, right? Okay, now we need to consider the second equivalent circuit to the right. So like here and this here. So this is B. Again, then I will disconnect this part, and this one here is B. And from B to ground. This circuit is the same as the first one. It's opposite way, right? Are they the same thing? This is R4, this is R2. So for this one, what is VTH2? What is this? Vs times R4 over R2 plus R4, right? How about RTH2? 2 and 4 are in parallel. Keep in mind, we need to reduce this one to a straight wire. Right? So this one and this, look. These two, this part, this terminal are connected to 1 point. So R2, R4 in parallel. Right? That's it. That's for the second one. So let me review the second one. That is B, and we have this, and we have here. Then this connect to the ground. So that is VTH2. This is RTH2. Then we put the load in between. This is RL. And we are going to use this one. So what is the current here? We discussed this before, right? And we have two sources. Is this one minus this, because we are looking for the current going this way. This one minus this, and divided by these three, add up together. Is this result the same as ours?
Yes.
Ours, when we calculate, in our previous result, VTH equals VS equals this one minus this, right? VTH1 minus VTH2. This is our result, equals this one minus this. Right? And we said the RTH equals these two in parallel, then in series. So exactly equal to this one and this one in series. So actually they are the same thing. Our method is the same as this one. But our method is directly reduced to one equivalent circuit. And this method reduced to two, then combine together. Okay, now let's plug into numbers we calculate. Okay. So the first one equals R1, R3 is equals 165. And the 2 and 4 in parallel is 179. And the voltage, the first one VTH1 equals 7.5. Why equals 7.5? That's easy, right? Because 1 and 3 are the same. Both equals 330, so they share the same thing, so they divided by 2. Right? And the B is different because one is 390, another one is 330. So this one equals 6.87. then the circuit will be look like this. And if we are looking for the load current, so we put the load here, then that is a series circuit. And this equivalent circuit is much better than the Wheatstone Ridge or bridge, right? That is look like complicated. This one is much easier. Okay. And the load current will be, that's trivial, easy to calculate. The difference between the two sources then divided by the sum of the three resistors. That's equals 1 or 2. Okay, any questions? In the whole, this one is more theoretical. In the homework or in the test, I don't believe I will give you this kind of, let you simplify this. But you need to keep in mind, what is the condition for this bridge to be balanced? That. Yes? These two multiplied together equals these two multiplied together. Right? Alright, the next one is this one, also very important. Let me state the problem first. Then we are going to find out a solution. We have a battery, right? Your cell phone has a battery. Suppose battery looks like this, and the battery has an internal resistance. It's not ideal, right? So we have an internal resistance. And this one is positive or negative. That is the equivalent circuit for your battery. Make sense? Now you connect this one to a load. This load can be, okay, light bulb or anything, right? This one. And this one is called R. We use I think we use the internal, I forget, let me see. S, okay, source. So this one. And this one is VS. Right? So that is the problem. We have a non-ideal voltage source, which means we have voltage, we have internal resistance, and we connect this source to a load. That is the problem. What we want is find out what is the power dissipated on the load. Can we do this? What is the power dissipated on the load? Series circuit. Everything is given. What is this? What is the power on the load?
The same as the power on RF.
No, you don't go too far. Okay, we'll discuss this one. We'll go step by step. What you said is correct, but not right now. What I want is the load, the power on the load. How to do this? That's nothing new. We know this before.
Yeah.
And we have the table, we calculate all the powers.
Yeah. E squared over
The power equals, for this series circuit, usually we use the current squared times R, right? Because the current is the same. So current squared times R. What is the current?
We don't have it.
We don't have one. We need to calculate. This is a series circuit. So that will be equal to what is the current?
I equals V over R.
Vs
Over R.
over Rs
Plus R.
plus Rl. Is this the current?
Yeah.
Right? Then current squared times
R.
Rl. Right? That is the load. That is the power dissipated on the load. Questions on this? You can do this, right? That's very easy. If this is in the test, that means I'll give you the point. You need to take it. My question is, if this one is given, but this one is a variable, and you can connect this anything to your battery. My question is, when this power takes the maximum? Look at this. Suppose if your load equals infinity, you do not connect it. This is battery, negative, positive. You connect nothing to your load, just open circuit. what is the power on the load?
0.
0, because you didn't connect it. Okay, let's see. This one equals infinity, this one equals infinity, this is squared, this is more infinity, so this one equals to 0, right? So if you don't have a load, the load equals infinity, then you get nothing. How about you short this? Have battery, you put your battery, and in the pocket you have keys, right? Okay, unfortunately the positive negative connected, short. What are you going to feel? Burn here, right? So you're going to maybe fire here. That's very bad. So anyway, this RL equal to 0. What is the power here?
0.
Equals 0. So we have fire here. What happened? Where does the power come
It's too
from?
much.
It is no, not much. It's 0. It's always the power is in here, right? From your battery, not from the wire, because not from the key. It's from the battery. Your battery will explode.
Yeah.
Right? So in this case, if your load equals 0, then no power. So if your load equals 0, the power equals 0. If the load equals infinity, no power. So there must be somewhere in between that we can take the maximum power, right? Right? So that is your conclusion. Right? If I draw something like this, so suppose this is the load, this is the power. I just get something. If the load equals 0, then the power equals 0. If the load equals infinity, very large, then the power still equals 0. Then this line must be something like this, from 0 to 0. So there must be somewhere that you take this load, right? The power takes the maximum. That is this power. What I want is when, in terms of this load, the power on the load takes the maximum. That is called max power transfer. That means this source transfers the maximum power to the load. If you short this, 0 transfer. If you open this, 0 transfer. When this one can get maximum power transfer to the load. And the conclusion is when this load equals this source. That's it. Mathematically very easy to prove, but I don't bother with you. You need to memorize this. When the load resistance equals this internal resistance, then this one takes the maximum. Does it make sense? Alright, now let's go further. What is this maximum? How large is it? Suppose this is VF, this is RF, this is RM. It says take the maximum. Okay, we agree. Then how large is it? Keep in mind, this one and this one will be equal, right? Right. What is the power on the load? Max.
Equals RS.
When this one equals this, right? So in this case, we are going to use the voltage squared over R. Right? We may use this one, or use R squared times R. Doesn't matter. Right? So suppose we use this one. What is the voltage on this one? Keep in mind, this one equals this.
VS over 2.
VS equals 2, right? Over 2. Make sense? Because this voltage divider, these two are the same. I'm same with you, we share the same thing, so each one get half. So VS over 2, that is the voltage squared, then divided by R. Right? So that one will be equals VS squared over 4R. That's it. And this, what is the R? RS or RL? Same thing, right? They must be the same. So you can use RS, you can use RL, so I just use R, because both are the same. Must be the same. When we take the maximum power. So that is one way to do this. Or the other way is I use the current squared times R. Let's try this one. What is the current? The current is voltage over resistance. This is R, this is R. So over, this is series circuit, over 2R, right? So over 2R, and then square, current square, then times R. Right? You evaluate this, still equals V squared over 4R. So the condition for the load to get the maximum power is when the load takes the maximum power from the source. When its resistance equals the source resistance. That's the first point. This is the condition for the load to take the maximum. Second one, what is the maximum? Equals the force equals the source squared divided by 4 times the resistance. Right? So those two formulas. Okay, now this one. What is the maximum power transfer to the load? First one, let's ask, is the maximum power transfer condition satisfied?
Yeah.
Yes? Because the load equals 50, the internal resistance equals 50, so it's satisfied. What is the maximum power?
1 over 4. I'm sorry, 1 over 2.
You can memorize the formulas, but not necessary. We understand this question, look like this. You think like this. What is the wattage on the load?
Okay.
What is the wattage on the
On the
load?
load, 5.
Because they are equal, right? Resistance equal, so it's 5. Then you use the wattage squared over the resistance.
5. Oh, never mind.
Right?
25 over 200.
So here, what is the wattage on here?
8.
5, right? Because this one equals this, so they share the same thing, so this is 5. Then 5 squared over 50. So that's it. That's we discussed very beginning. Right? The watts is law. What is squared over? So equals a half, right? 25 divided by 50. Right? So the wattage to the load is 5, and the power delivered is 5 squared over 50. So equals 1 over 2. 1 over 2, yes. The next one is C proposition. C proposition means if we have 2 sources, like in this example at the very beginning, the bridge, we have 2 sources. How to, like this one here. We have a source one here, and we have a circuit, and we have another source here. What I want is, what is the current? This is the current meter, right? What is the current on here? And the trick for this one is to use a C proposition. We consider only one first. Then we consider the other one only first. Then combine these two. What is the C proposition? If we have multiple sources, we consider any source only first, then consider the second one only, and then consider the next one only. You calculate all this result, you add up together. That's it. It's called C proposition. Make sense? Okay, let's look at this. And we have this 12, and we have this is R1, 2.7, and we have this R2 equals 6 and 8, and we have this one here, 6 and 8. This is R3, and this one is another source here, and this one equals 18. So V at 2 equals 18, V at 1 equals 12. What I want is the current. What is this current? So we have 2 batteries here, and that is what I want. How to do this? Is a C proposition. We only consider one source each time, right? For example, I consider this one only. That means this one is gone. What does that mean when it's gone?
It's irrelevant.
It's short, yes, perfect. It's short. That means this one here, I will redraw this, right? So this one here will be like this, right? This is gone. We want this current. And this one equals 2.7, this one 6.8, 6.8, this one equals 12. Can you calculate the current here?
Yeah.
Very quickly. How these three are connected?
The one in series, that's in parallel.
Parallel,
And
then
in series.
in series, right? So the current here will be equals to the source divided by, this is R1, and this is 2 and 3, then plus R2 parallel with R3. 2 and 3 in parallel, then R1 in series. Yes?
Yes.
Right. Now you plug into numbers, this one equals 12, this one equals 2.7, this one 6 and 8, 6 and 8 in parallel. What is it?
3.4.
3.4. If 2 are identical, you divide by 2. If 3 identicals, you divide by 3. The reason is, remember the example in the car, right? The wires, you have 10, you divide by 10, same thing, right?
1.9.
So 1.9, right? 1.9?
Yeah.
Okay, 1.9. This is K, this is V, so it's MA. 1.9 MA. So this one equals 1.9. What is this?
1.9.
This one equals 1.9, right? This is what we are looking for. Current divider. But the good news is they are the same.
Yeah.
So equals half
3.1.
of this, right? Yeah?
Yeah.
So this current here equals the first time, so current, the load the first time equals 1.9 over 2, so equals 0.95. The total equals 1.9, shared by this 2, divided by this 2, but these two are the same. So each one get half. Question on this? Are we done?
No.
No, we done the first one. Alright? Superposition, we need to do the second one. Alright, second one. How to draw the second one?
Just change the source.
Just change the source. This one will be straight, right? Alright, so what we have is R1 here, and this one will be R2 here, and this one will be R3, and like this. That is 18. That circuit is the same as this one, right? It's parallel and in series. We can do this, then we can do this. This one we use some trick, don't need to calculate much because they are identical. But this time, not identical. But we can still do this, right? Okay, what is this current? This current equals the total current here. Which one we are looking for? We are looking for this one, right? Then divided by this 2. Let me write somewhere. I don't know if you can see or not. Let me write this one. So IL2 equals this part is the total, then divided by this one, but this 2. So what is the total? The total is VS2 divided by R3 plus R1 parallel with R2. That is the total current.
R3 equals,
Yeah?
yeah.
Okay, then this is total current, then divided by this 2, right? So it will be R1 plus R2 on the bottom, current divider. I hope you still remember this. Right? What is on the top? We are looking for the current on R1.
R1.
What is on the top? R2, right? R2. Right? That's the formula. Then you plug in the numbers, right? And this one equals 18. This one is R3 equals 6.8 plus 6.8 parallel with 2.7. Then times R2 equals 6.8. Right? And 2.7 plus 6.8. And the result, that's lengthy, all right? So I just copied the result from here, right? So the first one is 1.97. We said 1.9, that's good, right? And that one equals 0.98. We said 0.95 still. And the second one is this, total. And this one equals 206. And the divided equals 0.58. So this one equals 0.58. Are we done?
Yes.
Yeah, we saw both of them.
We solve both of them. Then what's the next one?
Plus.
Add up together. Right? So that is what we want. So the total will be equals the first one source, okay, the current due to the first source plus the current due to the second source equals 1.98 due to due to here, right? Oh, 0.8 plus 0.58. So that will be equals 1.56 MA. So the result will be equals 1.56. Questions? You can see we go very fast, right? Looks like new, but nothing new, right? You just only one technique learn, use the superposition. You separate it as two. And you can solve one easily before. So you just add up these two together. You just like, we have, each problem has two problems. You just add up together, that's it. Right? This is troubleshooting, right? We are engineers, technologists. You need to solve some real problems. So the first thing is we need to understand We need to troubleshoot this thing. Right? And we need to analyze the circuit. We need to know the theories. Right? And decide a logic set of steps to find the fault. When you solve the problem, you need to give me the steps, right? In the homework, I mentioned, remind you next time you need to show me the steps. And this is the same thing. You decide the logic steps how to solve the problem. Then, following the steps in the plan, make measurement to isolate the problems, modify the plan if necessary. And example here. Give you this circuit, something wrong, and let you find out what happened. 15, 330, 470, 2.2K. The output voltage is 6.0. If you calculate, we already calculated as an example before, right? The result is supposed to be 8.10. The voltage at this point supposed to be equals 8.10. That is our theoretical calculation. But if you measure this, equals 6. So what happened? Anything wrong? First thing you think is you have meter connected, right? If you connect meter, then this number will reduce. Oh, that is possible. So you need to double check your meter. If your meter is something wrong, then it's fine. Suppose your meter is good. That means the input impedance is very large. It's a stiff voltage divider. Does not affect too much. So the meter is good. What's next? Okay, now let's recall the theory. How do you calculate the voltage here? Equals this source multiply this part divided by this one plus this one, right? So while this number is small, Is it possible because of this one is smaller? That means your battery is, instead of 15, you maybe have 12. Is this possible? Your car battery is dying, eh? Okay, then give you this small. Yes, that's possible. So you need to check your battery. How to check the battery? Can you just measure like this? No. When you measure your car battery, you need to disconnect it. Disconnect it from, for example, here or here. You can disconnect only one. You don't need to disconnect two terminals. Right? For example, you disconnect from here. You measure this one. If this one equals 15, okay, it's good. Maybe equals 12. Then if it equals 12, you still need to figure out if this 12 it will give you this 6 or not. Maybe it give you 7. That means you still have other problems in this circuit. Eh? Maybe not necessarily only one, maybe a lot. Okay, suppose this battery is good. Then what else? The resistors. Is because this one is maybe something wrong, right? Maybe the numbers is, so this voltage is smaller. So that means this part is smaller, right? Or maybe this one is too large. Right? So again, you disconnect the source, then you measure the resistance to make sure they are correct. So that is how we troubleshoot this circuit. You need to know the theory, although you don't need to really calculate the numbers, but you need to know what happened. All the formulas must be in your head. Does it make sense? Feel good? So I'll give you a circuit if there's something wrong. Can you fix it? Your car is not working, not starting. Can you try to at least troubleshoot before you bring to the store? At least you can check your battery, if your battery is good or not, right? Okay, so we have some review here. And loading. Everyone still remember what loading is? You have a meter connected or a load connected to the circuit. Okay? And that current passing through the load is called the load current. And the other remaining current is called the bleeder current. And this Wheatstone bridge, it has 4 arms. And what you need to memorize is the balance condition. Again, what is it? The multiplier of diagonal resistance must be equal. Okay? Thevenin's theory. Any two-terminal circuit can be reduced to only 2 components. One is the source, another one is resistance. What is that source? Definition? This is the open circuit voltage. Right? You need to open load to calculate the open circuit voltage. What is the resistance? First line, open circuit. Second one, all the sources must be set to 0. Right? If voltage source, then it must be equal to 0. Okay, the last maximum power transfer. What does that mean? Okay, what is the condition for you get the maximum power? The load resistance equals the source resistance. Then you know how to calculate the maximum power. Right? It's very easy. Right? Okay, the last one is superposition. What technique is this? Suppose I'll give you a circuit. There are lots of batteries inside. I ask you to calculate a particular voltage or a current. How are you going to do it? You consider each source, only one source each time, then add up together. Right? So that is only bring one big problem into several small problems. We don't have time. We don't have time to calculate to do this quiz. Right? I suggest you. This is online, right? On the website. So you do this. This question, I don't agree with the solution to this one. Right? The solution says none of the above, but I don't agree with this. So you can check this one. My solution is I believe it's C. Yeah. Right? Okay, that's it. We have midterm on Thursday, right?
Well, be Thursday. These Thursday.